that star is weird wasn't until about 32 years later, and this is probably the most famous World War II era document in math. It's Tate's thesis. I guess Korean War era. So Tate's thesis says that Hecke's condition sort of translates to something much more natural if we think in terms of the Adels. So more precisely, Tate shows that that condition star holds when there is a continuous map homomorphism, of course, on the Adel class group so I'm also going to call this map psi. And the connection between this psi and the old psi is the following. Such that if P is prime to the conductor, then I can take the Adel, which just has a 1 everywhere except in the P spot. I pick a uniformizer, and that's just old school psi of P. So it replaces Hecke's condition with something much more natural. And if you want to go, oh, and not only that, but there's a very sort of quick and very natural proof of the functional equation using Fourier analysis when you reinterpret the character this way. That's the other sort of major result due to Tate in his thesis. There's many other major results due to Tate. And the other thing this explains, the Fourier analytic argument sort of explains those extra gammas that show up in the functional equation, which I didn't actually write down for general Hecke character, in terms of just seeing them as Euler factors coming from the primes at infinity. And that point of view only makes sense from the Adelic side. What's up?
So in Hecke's condition, it's one side for all of the principal ideas, right?
What did you say?
You stated a little funny, like it should be one side that satisfies us for all of the principal ideas, correct?
One side that satisfies
that.
That's right. There exists. So I'll explain how to translate from a Hecke character to a Tate character. That might make it more clear. So. Right. So in other words, given psi, or sorry, yeah. What did I call my field? F, right? The thing that I called psi infinity before. So I guess your question is, does it depend on the choice of ideal? No, definitely not. Right? It'll just be Tate's map restricted to the infinite Adels, which are canonically just F insert R cross. Sorry. Great. So there's just one. I guess I don't understand.
In your definition, you said if you have a principal ideal,
right,
then there exists.
Oh, okay, yeah, thanks. So psi infinity should be independent of the ideal. Yeah. Okay. Cool. So by the way, in the literature, both sort of Hecke's type of character and Tate's are referred to both as Hecke characters and as Grossen characters. And some of the literature makes a distinction, and some of it doesn't. So I use those synonymously, and I think of these as the same. Okay, so these are Hecke L functions. So I have to tell you about L functions of elliptic curves. So F is still my number field, and I'm going to let E over F be an elliptic curve. Okay. I'm going to define an L function. So it's still a function of a complex variable. And I'm going to define it in terms of an Euler product expansion. So P is a prime of F. And I'm going to define it in terms of local factors that I'll call LP. each prime. So let me define those. So LP of ES will be the characteristic polynomial of a Frobenius at P. So this is some choice of Frobenius in the maximal unramified outside of the P extension. Acting on the Tate module of the curve at some prime L away from P. As I formulated that, this doesn't quite make sense, right? How does Frobenius know how to act on? How does Frobenius know how to act on the Tate module, right?
Everybody here knows what the Tate module is.
Oh, I can define the Tate
It might be
module.
work.
Yeah,
I don't know.
sure. No, I don't mind. So now let's just let L be any field, and E over L an elliptic curve, and I pick some prime number. I've called it little l that has no relation to big L. Then I define the Tate module TLE to be the inverse limit of E bracket ln. By this I mean the L to the n torsion points of the curve. They're not going to live in the field L. Like L could be like Q, right? But they're going to live in the algebraic closure of L because they're defined by algebraic equations.
So then if we have another prime,
Yeah, whenever we have a prime named something that smells like a P in some font, and another prime that smells like L, they should be, if I take the norms down to Q, I should get things that are prime to each other. That's sort of a general fact. And that's not just my notation. So I define this, what is the inverse limit with respect to? If I take an L to the n torsion point and I multiply it by L, it becomes an L to the n minus 1 torsion point, and that's the transition maps, right? Abstractly, as long as L is prime to the characteristic of, unfortunately, big L, right? This is isomorphic to the L-adic integers squared, because that's just how much torsion there is in the algebraic closure, right? But you don't want to think of it this way because this carries the structure of a Galois module. The Galois group of L bar over L knows how to act on this, right? Because they're algebraic, and this doesn't. But abstractly, you're looking at something almost like a two-dimensional vector space, except for you can't divide by L. Okay. So I've defined it in this sort of abstract way. But really, this is the same thing that Alex talked about a couple of weeks ago, right? So another way to think about this up to sort of some canonical factors is the exponential generating function of the reduction of E mod P. So it's counting the number of points on the curve. And the reason they're the same, which is somewhat complicated, is the Lefschetz fixed point formula, which tells you that if you want to know how many sort of fixed points the nth iterative Frobenius has, right, on the curve over a finite field, it's the same as looking at the action of the curve, computing traces of the action of the curve on Atoll cohomology. And it turns out that this Tate module is canonically isomorphic to a Tate twist of everything's named after Tate of the first Atoll cohomology. So that's kind of morally why this is the same as what Alex said, and I can give more detail about that later, but it's not important for that talk. So conjecturally, this L function deserves to be called an L function, which means, again, that it satisfies some functional equation, and even though a priori it should only be defined for large enough S, it's actually defined on the whole complex plane. That conjecture is known.